Hey game fans, you're watching The What If Machine, the GameSpot show where we investigate sci-fi in video games and find out how plausible it is in real life. This week we're taking a jaunt into deep space, with everyone's favourite space opera epic Mass Effect. Now, we've already discussed the aliens of Mass Effect in a previous video, check it out at the link on screen now. Plus, if you want to know how likely an alien invasion is, a la Mass Effect 3, just head on over to the XCOM episode from 2 weeks ago. Today, we're going to focus on, for me, the most attractive thing about the whole universe of Mass Effect. No, not Miranda, but the ability to explore the galaxy. So, how does this compare with reality? What's our real-life space travel like? Well, I caught up with Dr. Colin Wilson in his lab at Oxford University to find out. Before we got underway, however, I started by asking him what on earth that giant blue thing behind him actually is.
So this thing behind us, this is actually a wind tunnel where we simulate the winds on Mars, because we're trying to build parts of a weather station on Mars and we need to test it and calibrate it so we know what the data are it's sending back. So this is a Mars wind tunnel. Okay, that's pretty awesome. But what about the cutting edge of space exploration, Colin? Say we wanted to travel to another star system with current technology, how long would it take? We're currently sending a spacecraft to Pluto, which is one of the fastest spacecraft ever launched in terms of they put an enormous rocket behind a not very enormous spacecraft. And this thing's going at 16 kilometers per second. The nearest star is 7,000 times further than Pluto. So if you think it's taking us 10 years to get to Pluto, it would take tens of thousands, maybe 60, 70,000 years to get to the nearest star. So that's not like Mass Effect, is it?
Definitely not. And remember, that's the nearest star. Say we wanted to travel to the area of space where you find the Citadel in the Mass Effect universe, well, that's roughly 6,000 light years away. From Colin's calculations, we can work out that it takes roughly 14,000 years to travel just 1 light year. That means it would take 84 million years to get to the Citadel. Reckon you might be more than a little late for that council meeting. So, how on earth do they manage it in Mass Effect? What's the secret? Well, it's all down to a system of mass relays, technology which allows spacecraft to travel great distances faster than the speed of light. So, is there any plausible way to actually travel faster than light?
The first answer is no, we can't travel through space-time faster than light. So reducing your mass to zero does not help. Things like photons have zero mass, and they are obviously traveling at light because they are light, and that's as fast as they can travel. But there are some clever ideas. So there's a guy at NASA who claims that you could warp the field of space-time itself using some clever things, using large masses, using lots of energy, so that your little bubble of space-time would be moving across the universe faster than light. Because you can do that. You're not traveling through space-time faster than light, but he thinks you could maybe move this bubble of space-time which you're in across the universe, maybe at 10 times the speed of light. So now you're talking about getting to the nearest star in less than half a year, which is, feasible.
Wow, so 4.3 light years in half a year. That would still mean 600 years or so to get to the Citadel, but hey, that is progress. How feasible actually is this? It all sounds a little pie in the sky to me, if I'm honest.
Well, he's got a grant to demonstrate whether or not he can warp space-time in the lab. I mean, he's only looking for a tiny amount of change, but if he can do something measurable in the lab, then I think people will sit up and start to take notice. Until then, I wouldn't invest in it myself.
Okay, but what about taking a leaf out of Mass Effect's book? In the fiction, these relays work by creating a corridor in space-time between the 2 points. What about this approach?
Some people do talk about a shortcut between 2 places in the universe, and these are called wormholes. So these are like a different route through space-time, and potentially they could be much shorter, so that you don't have to travel 4 light years to get to the next star. You can travel on the shortcut instead. The problem is that it's not at all obvious how to make one. So people have come up with theoretical things where you have to move black holes around to specific places, but we don't even know how to get to the nearest black hole, let alone move it around at our whim. So again, I wouldn't hold your breath.
When the crew of the Normandy reach Mars in Mass Effect 3, or any other planet in the game for that matter, they suit up before heading down to the surface. On closer inspection, their suits are generally fairly tight-fitting. Tighter on some than others, it has to be said. Nothing like the iconic astronauts of today. However, it turns out that the Mass Effect approach of skin-tight spacesuits might be exactly what our future Mars explorers need. Colin explains.
Conventional spacesuits, the ones they use if they're going outside the space station, have quite a big structure and it's full of pressurized air. So although you're in the vacuum of space, inside your suit you have lots of pressurized air, so it's a bit like being on the Earth or something like that. But this means that you need a whole superstructure. You're carrying an atmosphere around with you. Whereas with these new generation Mars suits, the pressure on your skin is provided not by air pressure, but by elastic pressure. So these are rubberized suits. Potentially, you're doing a lot of work as you move around because you have to work against the rubber of the suit. So this is where the very clever anatomical bit comes in. If you imagine that, for example, when you bend your arm, this side of your elbow joint gets shorter and this side of your elbow joint gets longer, and so that's what you're having to work against, the rubberized suit. But they've defined lines of non-extension. These are lines you can draw on the body which don't get longer or shorter when you bend your joints. And by making those really strong, like out of Kevlar or something non-extendable, you can have a combination of the non-extendable fibers and the extendable rubber suits, and it looks pretty good too.
The good old Citadel, the galaxy's finest space station, a hub for galactic trade and politics. So, could we ever have a place like this in real life? Well, obviously we do currently have the International Space Station in orbit around the Earth, but what about something bigger? Something we could construct and then launch future space missions from? Well, I asked Erin if this is something that could actually happen.
That's definitely sort of the way people are approaching it now, that this is something that's going to have to be done. And again, this is a long ways down the road because we have to be able to come up with an efficient way of getting people up there to actually build the space station. But people are looking at different ways because you have this big sort of gravitational well around Earth. That when you're launching a shuttle, you need to get out of that, which is why, you know, we have all of these chemicals and just this massive boost. It's just trying to get out of that sort of hole that the Earth is in. And so if you're able to build something sort of outside of that can easily get out and build a space station that can launch spaceships from that, you know, that's sort of the way to go. And these space elevators are, you know, a way that people have been thinking about, where you can sort of transport things out of gravity to a more reasonable level where you don't need as much energy to escape.
One of the major challenges if you're wanting to create a space station where people live permanently is the lack of gravity. As Erin mentioned earlier, spending long periods of time in a weightless environment can cause significant damage to the human body. Fortunately, it is theoretically possible to create artificial gravity using rotation, a spinning space station if you will. However, it would require the structure to be really large. To create a livable environment, it's been estimated that a rate of spin of 2 revolutions per minute or less would be needed. So to produce 1 G, like on the Earth, the radius of rotation would have to be 224 meters or greater. If it was too small, then the centripetal acceleration at your feet could be significantly different from that of your head. This could be a tad uncomfortable, to say the least. And that's it for this episode of The What If Machine. Now, I know I didn't talk about biotic implants or space weaponry or a ton of other things, but I want to save these for future episodes as they are kind of common themes in science fiction. Next week is the final episode of the 2nd season, so don't miss it. I'll see you then.